themes to a bunch of things that we have been talking about. I'm curious to know whether there's some sort of exchanges of techniques possible between the meta-complexity realm and this realm. Okay, so we're going to talk about learning versus the deletion channel. I'll explain what that means. Just a brief outline of the talk. So I'll set up the problem. I mentioned it briefly before on Tuesday during the open problem session. I'll talk first about the inspiration behind the specific problem that I will present more in detail. So the inspiration is the realm of string reconstruction, what I would call string reconstruction, also known as trace reconstruction in the literature. And then I'll go on to graph reconstruction. And again, that means something very specific in the context of my talk. I'll talk a little bit about the bounds that are known. And I'll endeavor to sketch the very basic outline of the proof if there is enough time. And I'll just mention the generalizations that we have, which often involve substantial new proof ideas. So, talk to me afterwards if you're interested in knowing more about that. And then I'll have a couple of open questions at the end. All right. And I should mention that this is a joint work with one of my two co-advisors. So that's Andrew McGregor, who you might know from the more of the sort of sketching, streaming realm, but he has a whole bunch of work. Okay. So let me set up the problem. So if you are not familiar with the problem, or if you weren't paying attention on Tuesday, then I will just say that I always like to start with this because it turns out that I had been thinking about this from substantially before my time as a PhD student. About 5 years before I started my PhD, a friend of mine gave me what has remained the worst Christmas present I've ever received. So anyone who knows me knows that I like solving puzzles, but I really despise jigsaw puzzles. So with that being said, can someone think of what the worst Christmas present I've ever received might be?
Jigsaw puzzle. One with 2 pieces missing.
Amazing. And anything else? A jigsaw puzzle of what?
And jigsaw puzzle.
What?
And it's a completely blank.
Yeah, it's the White Album jigsaw puzzle. So if you know, so it's it was genuinely a 10,000 piece jigsaw puzzle of the White Album. For those of you who don't know, it's an iconic, wonderful album, but a horrible jigsaw puzzle, which is almost entirely white. And in fact, someone pointed out, maybe Russell, what my friend did to add insult to injury, as it were, is he bought 2 copies of this puzzle and then mixed some of the pieces together. This is a genuinely true story. So it turns out I've been doing sort of reconstruction work from way before, 6 horrible months later when we had finally kind of like come up with a version of that. I didn't know then that I would work on this. So so that's what you should keep in mind as I set up the problem specifically. So let me start by describing what string reconstruction means. So the main object of interest is going to be something called the deletion channel, which introduces some kind of noise or some kind of fluctuations in a string of interest. So imagine that you have an unknown string, any big string, if you like, that keeps on going through a deletion channel. So what does this deletion channel do? It keeps some of the bits of the string with some uniform probability. So it looks at every bit with the same uniform probability p. It keeps them with that probability, it deletes the rest, and it's concatenates everything left together into a new string. It's a subsequence of the original string. And that's what you get as an output at the end of the deletion channel. So for example, if this is your string, I'm going to represent the deletion channel by means of this sort of green rectangle. You might get the string, you might pass over the string once, it deletes these bits, and importantly, it concatenates them, and you get an output of this form. So this would be a single output from the deletion channel, and that's what we would call a trace. Okay, and then notice that the same string, of course, will, as you pass it more and more through the deletion channel, it will give you different traces like so. And then, and also, you would imagine that the length of a trace would be roughly concentrated around like p times n, if n is the length of the string, but occasionally you will also get quite different lengths of string. And importantly, you lose the contextual information of where each of these bits came from. So that's a critical part of this this project. Does that make sense? Like the idea of the deletion channel. Okay. So given the deletion channel, the string trace reconstruction problem is a learning theory problem. It goes back a while. It states what exactly you would believe. So if you have an unknown string here that gives rise to traces of this form, and you keep on, your only access to that string is by means of observing those traces and just the output. Then the question is, how many traces will you need in order to reconstruct the original string with high probability? The high probability will mean what you would think it means. So it's 1 minus 1 over poly n probability. Okay, so that's the trace reconstruction. So if you haven't seen trace reconstruction, I do want to say what like a fact that I quite enjoy about trace reconstruction. Can anyone think of a motivation for why trace reconstruction showed up in this? I know at least one of you has written a canonically like huge paper in this realm. So maybe don't answer if you know this already, but can someone think of why this problem has shown up or how?
The coding theory, right?
Yeah, exactly. In coding theory, and specifically, it was a problem that it was a question that was first asked by evolutionary biology, it turns out. Because you can roughly model this idea of gene sequences by means of, does anyone know what that reference is? Luca. Yeah, it's a Pixar movie called Luca. So Luca stands for least universal common ancestor. So that's the hypothetical being that led to all the, I guess, the mammals and maybe the arthropods or something that's the extant species in the world today. And if you think about the way that sort of a sequence of genetic mutations occur to have all current species in the world today present from Luca, then you might ask yourself, how do you reconstruct the genetic composition of Luca? And very reductively speaking, the way you would do this is you have a distribution of the current sort of traces of these gene sequences, and you can use that exactly to try and reconstruct the original sequence. If you think of the mutations as passing through a deletion channel, which is of course arguable. Okay. So yes.
Is this part around
so this talk, I should say, will not mention NCSP, but I'm happy to try to talk about it afterwards. Does trace reconstruction make sense? I'll talk a little bit about the history of the problem in a bit, but I also want to define graph reconstruction, which is the problem that I'm interested in. So now you have a graph deletion channel. It's substantially what you would think. You have an unknown n vertex graph, n node graph that's going to keep on going through a deletion channel. So that's our running example now. And it's going to keep the nodes of the graph, and you can think about alternative forms of the deletion channel, but let's just stick to node deletion for now, or vertex deletion, with some uniform probability p sub v, I have said to point out that this is vertex deletion, and it's going to delete all the others. It's going to then output the resulting induced subgraph. So that might be one particular induced subgraph that you get from this graph, and for consistency, we'll call this a trace as well from the original graph. And you might keep on getting a different sequence of these graphs. Now, I will mention, as with the string case, this is also a multi-set, and in fact, let's say you get a different set of deletions that lead you to this two-edged path. It would be reported just as a second copy of the local, right? Because you don't know. You can distinguish between the two in terms of where these came from. Does that make sense? So those are a set of traces, and so of course now you can ask the stochastic variant of the graph reconstruction conjecture, or like some variant of the previous problem where you just ask the same question. So if you have an unknown n vertex graph, and your only access to that graph is by means of a sequence of traces from the deletion channel, how many of these traces will you need in order to reconstruct the entire original graph with high probability? Yes, there is a question. Oh, sorry.
So you see like basically a histogram of the isomorphism classes of graphs, right?
Exactly. Of induced subgraphs, yes.
Yes.
Yeah.
Of the isomorphism classes of the induced subgraphs after going through this deletion channel.
Exactly. Yes. Yes.
It's actually similar to Marco's question when we talk about this times. So basically, I mean, if you get two isomorphic things, somebody actually makes sure that it's like, I don't know. I'm just curious if it's different. Suppose originally, we have vertices, have names, right? So in order to make sure you see the same thing, someone should come and, I don't know, wipe clean the nodes or something like that. I don't know. Like, how do you make sure that
Yeah,
I'm just trying to see if there's any way to take it, like suppose what we get this wedge or this
Yeah.
short wedge twice, so how do you, or how does, I mean, the problem ensure that we actually know that that's the same thing, because if these are different versions, somebody should like wipe the names or somebody should do something, right?
okay, good question. So if you were trying to code up this problem, you would have to then have some sort of subroutine that, depending on how you're storing the graph, it would have to apply some sort of random permutation or canonical representation of like different graphs of the same isomorphism class. You're absolutely right. And in fact, if we have time, we'll get to how that problem is slightly different from this one. But I'm saying in abstraction, you can ask this problem. This is a pure graph theory problem right now, right? Like I could have, independent of the question of how you actually sort of do a random permutation and report just the isomorphism class, this is a valid question to ask. So that's the variant that we're interested in. And in fact, related to this question, I will point out here that of course this problem becomes easy, for some sense of easy, if the nodes were actually labeled and these labels were inherited in the traces themselves, right? Because then all you would need is to make sure that you've seen every single node to appear. And you will get that by, by some sort of coupon collector argument with log n traces. So, everyone agree? Everyone so far?
You have to see every pair of them.
You would have to see every pair of nodes, I'm sorry, yes, but that's still the same, to determine whether there's an edge between them or not. Great.
Like, there's also something, like, there's a big open problem in graph theory called the graph reconstruction problem, right? And there's a Wikipedia page and everything.
Oh, yeah, it's that big, yeah, it has its own Wikipedia page.
Okay,
That's
so
true.
this is not that.
This is not that, so this is a stochastic version of the problem, so that's a good question. Talk to me afterwards about how these are related, but that is something on the graph reconstruction conjecture that claims that any graph is uniquely reconstructible from its deck. So what's a deck? A deck is the multiset of n induced subgraphs you get by deleting a single vertex in every single way from the original graph. So very wide open problem for 60 years. We know that it can be done for random graphs, and that's also something vaguely to keep in mind as we keep going through that. But good question, yes. Note that in that conjecture, the subgraphs you see are very large. They have n-1 vertices. Here you see about half if you think of P sub B as a half. Good. Okay, so I will come back very briefly. I'm going to go through this slide. So if you think about it, if you think about why this is related to the white elephant jigsaw puzzle, I don't have to tell you, but then a solved jigsaw puzzle essentially you can think of as corresponding to a graph. Let's ignore questions about whether this is a labeled graph or not for now. But essentially, if you think about the idea of like grabbing a bunch of pieces from this graph and trying to just sort of solve those pieces by themselves, that would correspond to an induced subgraph. And so in effect, what you're doing by means of that exercise is getting a bunch of samples from the deletion channel in exactly the form that I have suggested. So really, this is a simulation of the deletion channel instance. And so all I'm trying to tell you here is that if we can solve the trace reconstruction problem or the graph reconstruction problem, we have a way to deal with my horrible Christmas present. Okay, that's all the motivation I need. Okay. So let me give you a sense of the known bounds for these two problems. And so I'm going to have a sort of comparison between these two. So on the left, I'm going to talk about strings, n-bit strings, and on the right, I'm going to talk about n-node graphs. So for arbitrary strings and arbitrary graphs, for arbitrary strings, the state-of-the-art upper bound that's known for, so I'm only interested in remembering the sample complexity, the number of traces you need. The state of the art that's known is exponential in the 5th root of n. This is a result by Zach Chase during his time at Oxford. This is the best known possible result, but I will also mention an important result, which is exponential in the cube root of n, and that's a 2016 result by two groups of people. So Rocco with Ryan O'Donnell and Amingo Day, I think that was one of the papers, and then we had Nazarov and Paris also around the same time. They had this really beautiful, exponential in cube root of n upper bound that was known that stood for 4 years. And in fact, Rocco's paper went on to also show that this is actually tight for a very natural class of algorithms called mean-based algorithms, which essentially just sort of look at statistical distributions of where you expect the bit distribution to lie. So even though the second one is a weaker bound than the upper one, it is still known to be tight for a quite natural class of algorithms. Okay. But I mean, generally not good news, as you can see, it's a massive upper bound, particularly considering that the best known lower bound is just polynomial, it's n to the 3/2, roughly. And that's actually a different paper by Chase. I should say C28 and B over here, but so that's what's known for strings. For graphs, for arbitrary graphs, of course, you have, as I said on Tuesday, you have a sort of trivial exponential in n bound, because if you have that many traces, you're going to see the whole graph at some point, so you can output that. So one of our results matches that upper bound as well. We exhibited, two different graphs. I'll give you a quick reminder of how this proof goes in a sec, but basically there's two graphs which need exponentially many traces in n to distinguish between the two. So those are matching upper and lower bounds. Green suggests that the sort of like the tightness is known here. For ordered graphs, and that also goes back a little bit to Ilya's question before. So if you think of graphs as, it depends on the model you're using, but if you were coding up a graph, you would use an adjacency matrix. And if you think about that, it's a slightly different problem from the pure graph theory version, because there's some ordering information you retain in the traces. Using that sort of extra power or extra information from an ordered universe, we can improve the upper bound slightly. It's still exponential, but it's an exponential improvement is the way I look at it. I will also say that for random strings, random in the sense of there's a whole bunch of stuff I could have put in here, but I just wanted sort of some of the most canonical results for random strings. This is a paper by Nina Holden and others from Colt team. They show that a random string where you just draw it from sort of all 2 to the n strings uniformly at random can be reconstructed with exponential in the cube root of log. This is actually sublinear in n, but super polynomial, super polylog in fact. And you have a lower bound of about log to the log n to the 9 fourths. The tilde here represents like log terms. Okay, for random,
Neither of those are the state of the art.
these have been improved since then.
Yeah,
Okay, so
I mean, it's Ty Rubinstein has the log 1/5.
yeah. So that's the improvement on the upper one. Yeah, you're right. I don't know. This
There's a
had
general lower bound reduction where if you get a new lower bound for worst case, that feeds in, that gets a new lower bound for the random case by just a black box reduction.
I see. Okay, I never knew that this lower bound had been improved. So okay, so talk to me afterwards. I'm interested in that. You're right. I should have updated this upper bound. Yeah. So that's for random strings. For random graphs, we can show a log n upper bound. This is assuming that the deletion probability is a constant. Some of our results extend to cases where the retention probability, the probability with which you retain each of the vertices is actually sub-constant as well, but for constant retention probabilities, there's log n traces suffice. And that actually matches the sort of trivial log n lower bound, which is again the coupon collector lower bound. You need that many traces just to see every vertex. Okay. And then for sparse strings, there's different lines of work done on sparse strings depending on your notion of sparsity. So there is a 2021 paper by Andrew and a couple of others that shows this sort of exponential in log 2/3 of n times some cube root of a measure of sparsity. Here the sparsity is just the number of bits in the string. They can improve this result if every single one of the sparsely few ones is also separated by enough zeros. As you can imagine, then this becomes sort of like a better polynomial bound. As far as I know, nothing much is known about sort of like the lower bound beyond the trivial lower bound for sparse strings as well.
Wait, what do you mean by sparse?
Yeah, so here there's different lines of work that are done. Here the k is a measure of the sparsity. That k just means the number of ones in the
So
string.
when you consider a string that's all zeros except for 1, 1 to be sparse,
Yes.
okay, then don't you get an omega n lower bound? just from the pair where you have all zeros except for one exact in the middle versus.
Right, so I think this relies on you knowing what the value of k is beforehand or something like that. So,
I don't know what that means. You can just have a pair of strings where they each have a single one.
yes, so that's roughly that's roughly like sort of this this
No,
kind
but that's
of,
a sparse pair.
that is a sparse pair.
And you need n traces to distinguish between them.
Yeah, up to log factors, yeah.
No, just n.
Why do you need n?
This, I mean, you have to do a calc, I mean, it requires an argument, but that was the best lower bound before Nina and Russ lines, and the 5 quarters.
Okay,
And there was also complementing that, there was a very nice recent result by few people who showed an upper bound of n log n if the gaps between ones are at least logged in n.
yeah, K polylog, and that was recent, right? But that still relies on the number of ones being absolutely bounded or something like that, right?
No, just the ones are separated.
Just the
by
ones are separated.
Polylog many zeros.
I see, okay. So let me update this slide afterwards, so thank you for that. So sparse strings are sort of like better understood now. I guess there's a notion of sparsity in graphs as well, like the relevant notion here, the k over there in that upper bound is the arboricity of a graph, which is a fairly natural notion of sparsity. You can get sort of similar bounds for ordered graphs. Again, there's not much you can do with unordered graphs, but for ordered graphs, you can get some improvement. Okay, so yeah, we'll circle back to the sparse discussion afterwards, but let me give you, how much are we doing on time? 6 minutes left, okay. So I've already talked about the lower bound briefly. Of course, I'm going to rush through this slide. So this is just as a reminder, this is a theorem that says that you need exponentially many traces, even to reconstruct, even to distinguish between a pair of graphs with constant probability. You don't even need high probability, and even when you know the deletion probability is a half, and that was the sort of large cycle versus disjoint union of 2 cycles example, because there's an incredibly high probability of sort of like diametrically opposite points from the left one being removed, and an incredibly high exponentially high probability of sort of 1 point from each of those cycles being removed. Then you can somehow use that to finesse an exponentially lower bound to separate these two strings. Okay, let me give you a quick overview of an upper bound argument, because I think that's really sort of the interesting graph theoretic insight that we happen to find after sifting through a whole bunch of old papers, including an incredibly an old result that we were just flabbergasted by. So I'll try to give you a sense of that. So this is going to be the random graph upper bound that I'll try to sketch for you. The theorem that I'm trying to show is if G is a random graph and P of V, which is the retention probability for the vertices, is a constant, then you can reconstruct that graph with just log n traces.
Does random graph mean e.g. Gn1/2?
Exactly. So G is a graph that you have drawn from just the error of any Gn1/2 distribution. Okay.
Do you need 1/2 for anything?
You can do it for, so there's 2 probabilities, the parameter in the arbitrary, it can be any constant, and this guy can be any constant. That's the retention. Good question. Okay, so the proof idea here is if you had a pairing lemma, where if I gave you 2 different traces from the same graph, and you could identify the common vertices in those traces somehow. You could say, oh, this vertex V in the first trace and this vertex U in the second trace, they come from the same vertex in the original graph. And you could do this for all sort of common vertices in the 2 traces. This would be useful, right? You can imagine, why would this be useful in particular? That means that given enough traces where you're seeing all the vertices, you would be able to simulate a labeling of vertices across all the traces. Because you can always recognize the same vertex across all the traces, and you would get sort of n of these, and then you'd have, then you would have simulated a label. So I haven't told you how to do that pairing lemma yet, But all I'm saying is that once you have the pairing lemma, you're essentially done, because then you can come back to that sort of comment about it's easy when you also see your labels. Because once you have the labels, you can sort of stitch these together into a graph by just following sort of for every pair. If you have seen an edge between them, there is an edge. If you haven't seen an edge between them, there's no edge. And then you're sort of waiting, everything in the dotted lines are pairs that haven't appeared so far together in any of the traces. So you're just waiting for them to show up. So this would just be sort of log n traces again. Okay. So how do you pair? That's the idea. So the pairing lemma drops out of this this really nice lemma by Muller from the 70s. Here's what Muller showed. Muller showed that a random graph, in the same sense, G and half graph, has no identical subgraphs, I'll explain what that means in a sec, of large size, of size more than half the size of the full graph. And furthermore, all the subgraphs of large size are asymmetric. So the first one means that there's no sort of, you don't have a large subset of vertices here and a large subset of vertices elsewhere that induce isomorphic subgraphs, where large means at least or more than n over 2. And then asymmetric just means that you don't have any non-trivial automorphisms. Okay, so this would be a symmetric graph because you can just sort of reflect these four vertices about to map to each other, but that's an asymmetric graph because essentially if you're trying to map it into itself, there's only one way you can do it, the trivial automorphism. Okay, so why does this help?
Wait, quick question.
Yes.
Is that one way trivial to prove or no?
It's not an incredibly difficult proof, but it's not a straightforward proof either. Yeah. The original paper uses that as a lemma for a different thing, but that the lemma itself takes up like 3-ish pages or something like that. Okay, so now you know that all large induced subgraphs of a random graph look very distinctive. They look unique. So how do you use that for pairing? So let me show you the result with the temporary assumption where the retention probability is high. It's more than 3/4. Okay, why does that help? Because now here's the algorithm that you can use. You look at two traces, let's say induced on vertex sets V1 and V2, subsets V1 and V2, and you go out of your way as an algorithm to find the largest common induced subgraph between the traces that you see. Okay. So here's your full graph G, and then you have, presumably you've passed it through a deletion channel, you have subsets V1 and V2, you have the intersection. Oh, okay. I'll finish up very quickly. So, of course, that intersection has large size. It has size, about half of each of those. If you somehow happen to find larger subsets W1 and W2 that are isomorphic to each other, you would have contradicted Muller because they would have to have size bigger than the intersection, and so you can't do this. So that relies on P being at more than 3/4. So you've now identified the intersection as a set, but you can also now use the asymmetricity to map vertices exactly, pair vertices exactly with each other. There's no chance of you getting the wrong automorphism. Okay, so that lets you, that uses the pairing lemma that finishes off the proof for a large enough P. You have to do a little bit more, but I'm out of time, so I can't really sketch that proof here. Just 3 things I'll mention is that you can generalize these in a couple of different ways. So you can support edge deletions in addition to vertex deletions, where you have some probability of the edges being also deleted. It's a totally different technique. So if you're interested, talk to me. But it does involve sort of like pairing isomorphism-like properties against each other. As I said, you can look at vanishingly small probabilities. You can take little o of one probability. You can go all the way down to 0, but you need sort of polynomially small and 1/n retention probabilities as well. You still recover basically the same results. And instead of deleting, you can now support edges flipping into non-edges or non-edges flipping into edges. And in fact, you can combine all of these. So you can have a very general deletion channel that deletes vertices, then deletes edges, and then flips some of the pairs. And as long as you know all of the, all of those probabilities, or you don't even need to, you can simulate them, but you can, get by this problem with a small number of traces. Okay, time's up. I'm just gonna leave these three questions on the board. I said the first one before. The second one is that it seems to be that, we can either answer questions to be extremely hard. You need exponentially many traces in order to like recover something, or you need very few traces, log n traces to recover something. So there's a natural sort of middle question here that Rocco also asked me, and I don't have a satisfactory answer to that. Is there something that requires an intermediate number somehow? And also, of course, all of this requires you to go out of your way to do isomorphism testing, which is an incredibly time-consuming effort. So if you also cared about the time complexity, not just the sample complexity, can you do any better? Okay, sorry for going over time. So that's okay.
So the question that I have is for the string reconstruction problem, but I think you can sort of extend the question to the graph reconstruction as well. And I guess the question I have is that if say the algorithm who's reconstructing the string is allowed to output stars in its in constructing the string, and you just care about approximating the string well enough, like get some Hamming distance.
Yeah, okay.
So instead of going from like exponential number of samples, you get like is like, since you are not expecting too much of the algorithm, is it like you get like
No,
volume?
the better notion is edit distance, and that's a very nice question. I don't know about for graphs, though.
Yeah, so
I can't tell you about it for graphs. So if you have an answer to strings, you can,
No, it's a very good open question.
okay, there's no.
Yeah, but you definitely want edit distance,
Yeah.
because Hamming it can be.
Yeah, good.
so, I was just gonna say that for graphs at least, the lower bound construction of a big cycle versus two small cycles are sort of any two nearly isomorphic graphs that have a very tiny sort of edit distance between them. That seems to rule out, a bunch of things that you can satisfactorily say. So I guess depending on what you're asking, so if it's okay for your algorithm.
Small edit distance. If you have a pair that is hard to distinguish and they have small edit distance, that doesn't mean anything.
Yeah, so if your algorithm is allowed to output sort of one of those graphs and say, this is good enough for our purposes, then yes, but it's also in that sense, I would say that that's not maybe a super satisfactory thing, because those graphs are quite different are opposite in basically any natural graph theoretic property you can think of. But having said that, I don't know about sort of like, we commit ourselves to outputting a single graph, or in the case of string reconstruction, a single string with some high probability. And your question is sort of if we allow some noise in the thing that we output in some sense, can we do better? I don't know of current algorithms to do that.
So, okay, my question was, so there are like, I don't know how many graphs are there. It's like, once you account for isomorphism, is it like 2 to the n squared roughly?
Yeah, for sure.
Okay, so unlike the trace reconstruction, for the graph theory, you cannot say the question is equivalent to a pairwise question where you just want to distinguish between two graphs, or can you? Yes, I'm not.
Okay, not for random graphs, but for
Worse, okay.
yeah, so for worst case, you can, because you can still have a tournament at the end if you can distinguish between two graphs. Because all the bounds that we are getting so far are exponential, so then at the end you don't lose anything by just having a tournament structure.
It's equivalent to multiplying the factor of n squared rather than, okay.
Exactly.
Okay, sorry. Sorry, I'm not sorry. Thank you.
Okay, more discussion, or do people move discussion?
I am curious what happened with the puzzle. I think you realize.
6 months later, no.